We think of Earth as the gold standard for life, but from an astrophysical perspective, it's actually kind of mid. Vast portions of the surface are hostile, deserts of rock, ice, and permanent darkness where nothing can survive. This chart tracks the lifespan of a yellow dwarf star like our Sun. It gets hotter as it ages, and if we look at the remaining window for life, 70% of Earth's time has already run out. If Earth is merely average, what specific parameters would we choose to build a truly perfect world? Let's design a hypothetical super-Earth, Hestia, a world engineered from the ground up, using the strict laws of physics to maximize biological potential. By constructing this perfect world, we're going to expose how profoundly limited Earth's capacity for life really is. Standard yellow dwarfs like our Sun burn through their fuel too quickly, leaving evolution only a few billion years to reach its peak. Long-lived red dwarfs have a different problem. Their narrow habitable zones mean planets end up tidally locked, with one hemisphere boiling, the other frozen. Our perfect power source is an orange dwarf. It provides stable energy, low radiation, and a lifespan of 70 billion years. By anchoring Hestia to a star that lasts 10 times longer than the Sun, we guarantee life the time it needs to reach its ultimate complexity. Hestia will be a super-Earth, with 1.3 times Earth's radius and nearly double its mass. On the surface, you'd feel 20% heavier. That extra mass allows for a massive metallic core spinning in a liquid mantle. This creates a magnetic shield powerful enough to deflect the cosmic radiation that would otherwise strip the atmosphere away. We also need active tectonic plates. Without them, internal heat unloads in apocalyptic volcanic eruptions, turning Hestia into a 470-degree hellscape like Venus. We'll add a slight axial tilt and 4 small moons to create mild, stable seasons that keep the climate predictable while maintaining evolutionary pressure. These foundational physics choices lock in a safe, permanent baseline, allowing biology to take over the planet's surface. Earth's geography is limited by its megacontinents. Their deep interiors are trapped far away from water, creating arid dead zones and vast deserts. We can fix this by using highly fragmented tectonic plates to create an archipelago world. This maximizes coastlines and ensures that every single piece of land on Hestia has direct access to water. By setting the global temperature 5 degrees warmer than Earth's, we turn these millions of islands into highly specialized niches, covered in hyper-productive tropical rainforests. We also eliminate the pitch-black abyssal desert. Hestia's oceans are shallow continental shelves, where sunlight reaches the bottom everywhere, fueling life at every depth. By maximizing war coastlines and sunlit ocean floors, we've turned the entire surface into a high-efficiency biological engine. Hestia's heavy mass holds a much thicker atmosphere. High levels of oxygen and CO2 drive growth, while extreme humidity prevents wildfires from ever reaching a destructive scale. This oxygen-rich air supercharges metabolism. Predators and prey move with more explosive energy, supporting the development of massive physical bodies. The thick air also makes flight energetically cheap. Animals need smaller wings and less effort to stay airborne, even with the planet's higher gravity. This results in skies filled with colossal animals that never need to touch the ground, communicating across thousands of miles through the dense, sound-conducting air. This thick atmosphere effectively functions as a vertical ocean, providing life with an entire extra dimension to inhabit. Earth hosts roughly 9 million species. Hestia, with its vast surface area and millions of isolated island laboratories, could support hundreds of millions. When you provide tens of billions of years for trial and error across these millions of habitats, the emergence of intelligence transitions from a remote possibility to a statistical likelihood. Hestia could spawn multiple, parallel civilizations evolving simultaneously on different island arcs, each developing their own empires without ever knowing the others exist. To these beings, Earth would look like a hostile rock, a frozen, desert-filled planet with a sun that's already dying. This world is consistent with everything we know about physics. Among the quadrillions of planets orbiting orange dwarfs, the probability of these exact conditions converging is remarkably high. Looking at the stars, we must realize Earth is just a baseline. The true biological paradises are out there, teeming with life in the dark.